Over the past year, I have given 2 presentations at the Graduate Physics Colloquium at Baylor. Although these presentations were on different papers, they have an overall theme, and that is to argue that quantum mechanics is both consistent with itself and that it can be consistent in a way that is compatible with Lorentz invariance. So basically, in this video, I'm going to be sewing these 2 presentations together. So I'll first give you the presentation on the paper, how quantum mechanics can consistently describe the use of itself, and hopefully this will lead nicely into the second presentation on the paper, Peaceful Coexistence, examining Kent's relativistic solution to the quantum measurement problem. So the first presentation I'm giving today is based on a paper by Lazarovici and Hubert titled How Quantum Mechanics Can Consistently Describe the Use of Itself. I'll first give you a little bit of background to this paper. In December 2018, Quanta magazine made the rather sensational claim. A thought experiment has shaken up the world of quantum foundations, forcing physicists to clarify how various quantum interpretations, such as many worlds and the Copenhagen interpretation, abandon seemingly sensible assumptions about reality. Quanta magazine made this claim in the light of a paper also published in December 2018 by Fraujiger and Renner, claiming that quantum theory cannot consistently describe the use of itself. Fraujiger and Renner defend this thesis by arguing for the following claim, that there are 3 basic assumptions of quantum mechanics that form an inconsistent triad. The first assumption is if quantum mechanics predicts an outcome x equals psi with probability 1, then this outcome will occur when the measurement is carried out. The second assumption is measurements have a single outcome from the viewpoint of the agent carrying out the measurement. And the third assumption is different agents applying quantum mechanics make non-contradictory predictions for the same experiment. Fraujiger and Renner claim that these 3 basic assumptions can't all be true at once. However, they made a mistake. So I will be presenting Lazarovici's and Hubert's analysis of why Fraujiger and Renner's argument fails. So what led Fraujiger and Renner to conclude that quantum theory cannot consistently describe the use of itself? Well, their argument is based on an extended Wigner's friend thought experiment. Here we have 2 friends, friend F in lab L and friend F bar in lab L bar, and we also have 2 Wigners, Wigner W and Wigner W bar, who perform measurements on lab L and lab L bar respectively. Now in this thought experiment, friend F bar first throws a quantum coin, and depending on its output, she sends a particle in a particular spin state to friend F. The rule is, if the coin lands heads, then F bar sends a particle to F in the spin down state in the Z direction. But if the coin lands tails, F bar sends a particle to F in the horizontal spin X direction. Then friend F measures the spin state of the particle she has received from friend F bar, and friend F always makes her measurement in the Z direction. So in the case when friend F receives a particle in the horizontal spin X direction, she can measure the state either to be in the minus a half spin Z state or the plus a half spin Z state. After friend F has made her measurement, Wigner W bar performs a measurement on lab L bar, which I will shortly describe, but for the time being I'll just say that this measurement outcome can be either fail bar or OK bar. But in either case, once W bar's measuring device has measured lab L bar, Wigner W bar becomes consciously aware of the measurement reading, which Fallacy and Redei indicate by giving Wegener W bar a speech bubble stating the measurement outcome. Finally, Wegener W performs a measurement on lab L, somewhat analogous to the measurement W bar performs on lab L bar, so he can either get fail or OK, and again a speech bubble indicates Wegener W's conscious awareness of his measurement. So what is it about this thought experiment that leads Frauchinger and Wegener to conclude that quantum theory cannot consistently describe the use of itself? Well, their argument is based on 4 claims. Firstly, they argue that if friend f obtains the result z equals plus a half, then the coin toss must have been tails. Secondly, they argue that if Wegener W bar obtains the result OK bar, then friend f must have measured the particle to be in this state z equals plus a half. Thirdly, they argue that if the coin landed tails, then Wegener W obtains the result fail. And fourthly, they argue that the outcome OK bar for W bar and OK for W has positive probability and will thus occur after sufficiently many trials of the experiment. Now it is fairly easy to see that claims 1, 2 and 3 imply 5. If Wegener W bar obtains the result OK bar, then Wegener W must obtain the result fail. And this obviously contradicts claim 4. But as Lazarovici and Hubert show in their analysis, claim 3 is in fact false. But in order to understand what's really going on, we need to consider each of these claims in turn. So let's look at claim 1, that if friend f obtains the result z equals plus half, then the coin toss must have been tails. Now this is fairly easy to verify, for if friend f bar gets heads, then she will send a z equals minus a half particle every time, and so friend f will have to measure the z equals minus a half spin state. It is only when friend f bar gets tails and sends the particle in the positive spin x direction that friend f has any chance of getting the result z equals plus a half. Thus when this happens, friend f knows that the coin landed tails. Establishing the validity of claim 2 is a little more involved. So we consider the state of the measuring device and labs from the perspective of Wegener W bar. Now, as I mentioned in passing, the coin that friend f bar tosses is a quantum coin. That is, it is initially in a superpositioned state, which Frauchinger and Wegener take to be root a third heads and root 2/3 tails. And in the thought experiment, Wegener W bar knows this initial state of the coin. Incidentally, Lazarovici and Hubert in their analysis introduced the bold typeface for the root 2/3 tails state in order to keep track of what initial coin toss preceded the measurements Wegener W and Wegener W bar make. Now once the coin interacts with the environment, entanglement will occur, and so Wegener W bar will calculate that the combined system of the particle has evolved to the following, which they abbreviate like this. But we know that we can write the particle in the positive spin x direction in terms of a superposition of the particle in the z equals plus a half state and the z equals minus a half state. So Wegener W bar determines the state to have evolved into this. Now we are in a position to describe the precise measurement Wegener W bar makes. His measuring device measures the state of the lab L bar with respect to the basis of states OK bar and fail bar, which I've indicated here. Anyone familiar with von Neumann's measurement scheme will be able to work out how the state of the lab L bar gets entangled with the state of W bar's measuring device. So if this is the ready state of the measuring device, it will get entangled with the lab state like this, and the ready state will get entangled with the tail state like this. And now Wegener W can incorporate this evolution into his calculation of the overall state of lab L bar and his measuring device, obtaining this rather complicated looking expression. Now this line here comes from the heads branch, and these two lines here come from the tails branch. However, we see that this expression can be greatly simplified. So we see that claim 2 is true. Now we come to claim 3, the one in which Fauchinger and Rayner are mistaken. Now Wegener W's measuring device measures the state of the lab L with respect to the basis of states OK and fail. And as in the Wegener W bar case, we can work out how the lab L gets entangled with Wegener W's measuring device. So if we make a bit more room here, we can insert the ready state for Wegener W's measuring device into the overall state of the combined system. And just as in the Wegener W bar case, we can work out how the -1/2 lab state gets entangled with Wegener W's measuring device, and how the +1/2 state gets entangled with it. Substituting this into the combined state, we get this horrible expression, but after a bit of simplification, we get the following. And the important thing to note here is that the item in bold is the term which Lazarovici and Hubert emphasize results from the branch in which the coin landed tails. So it's wrong to say that if the coin landed tails, then W must obtain the result fail. As for claim 4, we see that this is true, and the probability of the outcome OK bar and OK is 1/12. So why do Fauchinger and Renner draw the mistaken conclusion that if the coin landed tails, then W must obtain the result fail? Well, in order to show that Fauchinger and Renner are mistaken, Lazarovici and Hubert consider a Bohmian interpretation of quantum mechanics. Now with claim 3, Fauchinger and Renner make this claim based on the calculation that friend F bar would make, whereas Lazarovici and Hubert show this claim is false based on the calculation that Wegener W would make. If both friends F bar and Wegener W faithfully apply quantum mechanics to the situation, then Fauchinger and Renner would have proved quantum mechanics to be inconsistent, for it is assumed that for consistency, different agents applying quantum mechanics make non-contradictory predictions for the same experiment. So Lazarovici and Hubert need to show that the calculation that friend F bar makes in the Fauchinger and Renner's paper commits some fallacy. In order to identify this fallacy, let's briefly review the calculation from Wegener's perspective. He knows the coin is initially in a state of superposition, and as a result, the spin particle will become entangled with the state of lab L bar. Now, according to a Bohmian interpretation of quantum mechanics, when the coin lands tails, the particles go into the tails configuration, but the pilot wave corresponding to the heads branch, even though devoid of particles, can still affect the future dynamics of the system. Now Faujinger and Renner forget this. So they have friend F bar collapsing the state to this. But this is not a valid application of quantum mechanics according to the Birmingham interpretation. But if friend F bar does make this mistake, we can see how she would conclude claim 3. For in the correct calculation, you will recall we had this line from the heads branch cancelling with this line from the tails branch. But if you fail to take account of the heads branch, the cancellation no longer occurs, and you end up with this expression. And when you allow this to evolve, you end up with this. And so we see that according to the calculation in which F bar mistakenly fails to consider the empty heads branch, Wigner W has to measure lab L to be in the state fail. Because of this fallacy, Lazarovici and Hubert claim that Faujinger and Renner's extended Wigner's thought experiment does not support their primary thesis. However, Lazarovici and Hubert do not think that this thought experiment is without value. Rather, they suggest that it shows that quantum mechanics is not Lorentz invariant. That is, it is false that all Lorentz frames are equivalent in evaluating the predictions of the theory. To see why they might draw this conclusion, recall that Wigner W bar calculates the combined state of lab L bar and his measuring device to evolve to this before he makes a measurement, and from this state he can calculate that he would get the result OK bar with probability 1/6. But if we now consider the entangled state, which now includes the state of lab L as well, we see that if Wigner W bar makes his measurement first and gets the OK result, so that we can suppress these two terms here, then the probability of the result OK bar will be 1/2, because these two terms have exactly the same form. But because Wigner W and Wigner W bar are space-like separated, whether Wigner W makes the measurement first or Wigner W bar makes the measurement first will depend on which Lorentz frame we are in, and hence different Lorentz frames will make inequivalent predictions of the theory. However, I'm not at all sure that Lazarovici and Hubert are justified in drawing this conclusion about a non-Lorentz invariance. In their analysis of Faujinger and Renner's argument against quantum theory consistency, Lazarovici and Hubert claim that their analysis will apply to any single-world quantum theory without fundamental collapse. However, although they go on to show that their Birmingham interpretation of quantum theory is non-Lorentz invariant, it is by no means obvious to me that they are justified in claiming that every single-world quantum theory without fundamental collapse is non-Lorentz invariant. For instance, the physicist Adrian Kent has recently suggested a single-world quantum theory without fundamental collapse, which is supposed to be Lorentz invariant. So I think Kent's model suggests that quantum mechanics can consistently describe the use of itself and do so in a way that is also Lorentz invariant. To conclude this part of the talk, I think that Lazarovici and Hubert successfully refute Faujinger and Renner's argument that quantum mechanics is inconsistent, but I don't think they succeed in showing that every single-world interpretation of quantum theory is non-Lorentz invariant. So that brings me to my presentation on the next paper, Peaceful Coexistence, examining Kent's relativistic solution of the quantum measurement problem by Jeremy Butterfield. So what follows is going to fill out some of the details from the penultimate slide which I just showed you, which is this slide here. Now, the reason why I'm interested in this is because I'm doing a doctorate in philosophy, and I'm interested in the philosophy of Aristotle. And I think Kant's account of the measurement problem is in some way amenable to an Aristotelian interpretation of reality. So in Aristotle, things are ordered towards some end, and there's something about Kant's theory which I think is amenable to such an interpretation. However, I think, as far as I know, Kant has no interest in Aristotle, and he might think that I'm completely butchering his account of the measurement problem by trying to look for sort of an Aristotelian spin on what he says. But in this talk, I'm not really going to talk about my own philosophical interests with Aristotle, because I think Kant's relativistic solution to the measurement problem has great merits just in its own terms, regardless of what other kind of ontological assumptions you might want to impose upon what Kant says. So first, give you an outline. So first, I can examine the possible conflict between special relativity and quantum theory. And so the source of this conflict is the experimental violation of Bell's inequality. Then I will consider Shimney's proposal for peaceful coexistence via the distinction between outcome independence and parameter independence. Then I will look at Butterfield's critique of Shimney's proposal. Then I'll consider Butterfield's appraisal of Kant's proposal to the relativistic solution to the quantum measurement problem. And so Butterfield thinks Kant's proposal fares much better than Shimney's. But I also have to look at the consistency of Kant's theory with quantum theory and the consistency of Kant's theory with special relativity. So let's look at the possible conflict between special relativity and quantum theory. So it seems that they might be at war, and the source of this conflict is Bell's inequality theorem. So if you need a reminder of what this says, so really what you consider is a spin singlet, that two particles in opposite spin states as they're superimposed on one another, and one particle is sent to Alice and another particle is sent to Bob. So if they make the measurement in the same axis, they always measure opposite results. So if you change to the spin x-axis, they'll always get the opposite results. Now this might be a worry from a special relativity point of view, because it seems to violate locality. So one way to address this problem would be just to say, well, we have hidden variables. So here you have these variables for particle 1, these variables for particle 2, and you notice here you have particles, the variables for particle 1 and the variables for particle 2, and you see that they have opposite signs. And so this might be a way of preserving locality, because all the information is encoded locally in the particle. However, what Bell showed is that if you have such hidden variables, then you have to have this inequality being satisfied. On the other hand, quantum mechanics indicates that the probability should look like this, where theta AB is the angle between Alice's measurement and Bob's measurement. And so if you plug in a value of theta AB equal to 2 theta and theta AC equal to theta CB, and take theta to be pi by 4, then we get 0.5 is less than 0.292. That's if Bell's inequality really held. And you may think that quantum theory is weird, but it's not that weird, that we can't have a hidden variable theorem, hidden variables according to Bell's inequality. This is what it seems to show. However, Shimney, he proposed that, well, maybe things aren't quite as hopeless as Bell makes it appear. So he thought that we could identify the culprit. So Shimney, he asked, does Bell make a locality assumption that can be violated without violating special relativity? And Shimney said, yes, he did. And so to consider Shimney's analysis, he considers the quantification over these terms, where lambda is the physical state variable, x and y are measurement settings, and capital X and Y are measurement outcomes. And Shimney says that Bell makes the following assumption, that the outcomes X and Y are statistically independent. However, in this equality, Bell makes two implicit assumptions, outcome independence and parameter independence, which I'll explain shortly. But the point is, Shimney claimed that you could have a violation of outcome independence but still be compatible with special relativity, whereas violations of parameter independence would not be compatible with special relativity. And so the actual meaning of parameter independence is that we call your physical state, and this is the actual measurement that is made, and this is measurement outcome. So this is well defined, so regardless of what goes on at the other measurements that we indicated by y, if you sum these two values, the outcome of y and the outcome of not y, then this is not going to affect this value here. You always get the same result. So this probability is well defined and is independent of the y measurement. And outcome independence is just saying that, assuming that this is well defined value here, then if you just assume that this is going to be statistically independent from this random variable. But in this outcome independence, you don't make any assumptions about parameter independence, so you have to have the y here. So what's Butterfield's concern? Well, Shimney analyzes Bell's theorem in wholly non-relativistic terms. Now, this might seem a little bit strange. If you're kind of trying to show that two things are consistent with one another, you actually might want to actually say something about what you're talking about. But really, Shimney really looks at quantum theory itself rather than having any regard for special relativity. So there doesn't really seem to be any intersection between what Shimney is really saying about special relativity. So that kind of raises concerns. But also, Shimney says that outcomes can't be influenced non-locally, but Shimney doesn't say what he means by outcomes. And so Shimney is really sidestepping the whole measurement problem. So the measurement problem is, if the wave function is something physical rather than something epistemological, what happens to the wave function when a measurement occurs? So what happens compatible with special relativity? So for instance, if you had, say, like a Copenhagen interpretation of measurement, then if Alice is making her measurement and Bob is making his measurement, and there's a question about who actually collapses the wave function. Is it Alice or Bob? Because in some inertial frame, Alice makes the measurement first, and in another inertial frame, Bob makes the measurement first. So this seems rather puzzling. Can we really accommodate special relativity and quantum theory together? Butterfield thinks that Kent's proposal is much more promising. So what Kent proposes is that physics plays out between hypersurfaces S0 and S. And then what you do is you take an initial quantum state psi 0 defined on S0, and then you unitarily evolve it to the state psi s on the final hypersurface S. And what you do is, given this final state psi s, you also have an operator on it, a Ts, which is depends on the energy momentum tensor, and you just choose one possible mass energy distribution, Ts of x, according to the Born rule. So it's like you make some notional measurement. So it's not supposing that he actually saying that there is some kind of measurement that's made, but it's just a kind of a mathematical technique to sort of show how you get your history. This is our fictional measurement that we get, that are highlighted in purple, and then for point y between S0 and S, its energy momentum is given by the expectation value of the energy momentum tensor at y, but importantly, it is conditioned on the mass density being Ts of x outside of the light cone y. So we are conditioning on this information here and this information here, and we throw away this information here when we're working out the energy momentum expectation value here. And something to note about this theory is that it appears to be Lorentz invariant, so the information on which the energy momentum of y is conditioned is Lorentz invariant, because we're using this light cone to tell us which information we have. Kent goes on to consider a toy model for the wave function collapse. So this you can think about really what is happening when a measurement is made. So in this very simple example, Kent supposes that you have two mass locations situated at x1 and x2 with corresponding wave function psi1 and psi2, and he supposes that these two mass locations are in superposition with one another. So you have this superposed wave function psi0, and we appropriately normalize it so that a squared plus b squared equals 1. And Kent supposes that you have a photon that flies in and it interacts with these two mass locations. So initially you're going to have a joint wave function of this expression here. So this direct delta is for the photon, and this superposition is just for the superposition of the masses at x1 and x2. And then you evolve your wave function further, and things are going to get entangled. So when you work out the wave function after this interaction, you see that this minus has turned to a plus, so the photon is now going in the opposite direction. But the other possibility, the photon hasn't yet interacted with system 2, so it's still going in the same direction, so you have the minus sign here. And then as you evolve further, the photon finally interacts with the second system. It's going to be useful to make a note of this distance here to get you down to here. This is going to be a significant point in Kent's account of wave function collapse, and so we can work out the joint wave function now. So now that the photon that interacts with the x2 mass location, that's now going in the opposite direction. So how does Kent use this account to determine what the mass density is at particular points in sort of the world history? So he supposes that the photon actually that the measurement is actually measured to occur on at this point, which would indicate that the photon had interacted at mass location x1. And so for mass density distributed, so for times t less than 2 t1 minus t2, so this is at this point before, so this is the point where the photon interacts with the second mass location. So if you make your work out your mass density at this point, then the mass density is going to be distributed according to psi y squared, with a proportion of a squared localized around the y equals x1 location, and a proportion of b squared localized around the y equals x2 location. So it's a bit confusing with the x here and the y there, but anyway. So, and to see why this is the case, you just say standard quantum. This is really what you get from just standard quantum theory. And so, and you see here, when you condition on here, there's actually no information about where the photon interacted with the system, so that you just get exactly what you'd get in standard quantum theory. Again, there's no information here about the particle interaction, so you get a squared proportion here and a b squared proportion here of the total mass. So for times when the t is greater than 2 t1 minus t2 and less than t1, a proportion a squared of the total mass system is going to be distributed around x1, and nothing is going to be distributed around x2. So to see why this is the case, we consider now the light cone. So here, the information here, there's absolutely no information, additional information beyond standard quantum theory on which to work out the value of the mass density here. So you're just going to get the usual result, so which will be a squared. However, at this point, you see, when the value is calculated beyond this point here, then you're going to have information about where the photon interacted with the hypersurface S. So when you're here, you definitely know that there's going to be no interaction here, so there's going to be nothing here for the photon to interact with, but the photon you're going to know that the photon is going to interact here. So, but at this point, from this perspective, you know that there's going to be no mass is going to be distributed around x2. There's going to be nothing for it to interact with. And then finally, when t is greater than t1, the full system is going to be distributed around x1 and nothing is going to be distributed around x2. And again, to see this, you just now when you do your conditional expectation on the information here, you see now you know that the photon did interact with the mass located at x1, and so there's nothing that's going to there's going to be no possibility of any further interactions with the location at x2, and it's just going to be the same. That from here you know there's going to be you've got the information there, so we work out on condition of this happening that there is nothing here. So Butterfield goes on to consider the Kentian toy model of a Bell experiment. So rather than considering particles that are spin up and spin down, Butterfield considers a situation where you have an entanglement of matter located at these locations x1 and x2 and x3 and x4. So the wave function is going to be, the joint wave function is going to be this entanglement here, where psi I is localized around xi. Now YL and YR are the spatial coordinates of the left and right systems respectively. And again, we have a squared plus b squared equals 1. And so this really sort of captures or something of the Bell type experiment. And so what you consider is a photon comes from the left and a photon comes from the right. The left photon interacts with the left system and the right photon interacts with the right system. And then a notional measurement is made on S, which registers whether the left photon is reflected from x1 and the right photon is reflected from x4, or whether the left photon is reflected from x2 and the right photon is reflected from x3. So we assume that it's actually case A that occurs. Then at a space-time location on S prime, shortly before the left photon interacts with the left system, the mass density on S outside the light cone determines that the photon will be reflected from x1, because you see we have this information in here. So we know that the photon on the right interacts with the x4 location, so we know that the photon on the left is going to interact with the x1 location. And there's going to be a similar story for the right system. So we see that according to standard quantum mechanics, that when you make this prediction, you're going to predict a proportion of the matter being located at x1 with probability a squared. There's a proportion of a squared of the matter would be located there according to standard quantum mechanics. Whereas in Kent's account, so when it's sufficiently close, you're going to know for certain that with probability 1 that all the mass is located in this left-hand system at x1. So you might worry that you actually get Kent is offering a theory that is distinct from standard quantum theory. I'll try to show you why this in itself is not a worry, but we have to admit that quantum mechanics and Kent's theory give different measurement probabilities. Another thing worth considering is the issue of outcome independence, which was which Shimley considered, where you assume that x and y are statistically independent. Now it's fairly easy to see that any deterministic theory satisfies outcome independence, and furthermore, so given lambda equals Ts, Kent's theory is deterministic. So this means that, unlike quantum mechanics, Kent's theory satisfies outcome independence. But this, although Kent's theory is distinct from standard quantum theory, this is not necessarily a problem, and because we have this expression here, this is really telling you that experimentally that you wouldn't be able to tell the difference between Kent's theory and standard quantum theory. So here we have the standard quantum mechanical probability. So here we have Kent's probability, and here we have the space of all possible mass density measurement outcomes on S. And this is something that in principle that we can never know. So the best that you can do is that you take the weighted probabilities according to the measure on TS. So given your state psi S, there's going to be a distribution of possible mass densities that you could measure on your final hypersurface, and you calculate these probabilities in terms of the Born rule, and then it seems that Kent's theory is experimentally indistinguishable from standard quantum mechanics. So what about the consistency of Kent's theory with special relativity? So here we ought to again consider parameter independence. So if parameter independence were to fail, then we might worry that this really would be a problem for any account of physical reality. So here is not going to be well defined. So this is a probability that you have outcome X when you have your measurement setting set to X, and this describes your physical state. And if you have parameter dependence, and this is not going to be well defined because someone else might make a measurement at position Y, and what's going to happen is that you're going to get different values here depending on what, say, if this Y is what Bob measures, that Alice is going to work out different probabilities based on what Bob sets his parameters to. So this is so long as Alice knows lambda. So we just consider this briefly in the spin up and spins down singlet state. So they, if they're measuring in on the same axis, they'll always get opposite values. But if they measure, on different axes, it looks like if parameter dependence held and Alice knows lambda, then in principle she could work out the measurement Bob performed, and hence Bob could send messages to Alice faster than the speed of light. So this seems to be like a big red flag if you want to maintain special relativity. However, according to Kent's theory, it is completely impossible for Alice to know that lambda equals Ts. So from that point of view, even if parameter independence is violated, it doesn't seem like a complete disaster because there's still no information that Bob could convey to Alice. So they're going to make the following points about whether Kent's theory is consistent with special relativity. So it does appear that Kent's theory is Lorentz invariant. Now Butterfield thinks that it's an open question of whether Kent's theory violates parameter independence, but personally I think that Kent's theory does violate parameter independence as far as I can see, but I can't see why this would violate the spirit of special relativity, given that it's intrinsically impossible for Alice to know what this parameter lambda is. Because this means having to know what the mass density is on this final hypersurface, and this is going to be impossible in this framework. And we kind of assume that Alice doesn't have premonitions of the future. So Butterfield also thinks that Kent needs to address a no-go theorem of Kohlberg and Renner et al. So the no-go theorems are really saying that you can't have everything that you really want for a theory. So this no-go theorem, it supposes that you have this equality here. So this is really just saying that this hidden variable theory is experimentally indistinguishable from standard quantum mechanics. So here we have an observable O hat, and we have an eigenspace projector of O hat, and this probability here is just a standard quantum mechanical probability, this expectation value of the projector E hat, and you have lambda, which is a hidden variable. As I put hidden in quotation marks here because I mean we're not, although TS in Kent's example is intrinsically hidden, you don't necessarily need to commit itself to being a hidden variable, but really it's kind of like a variable that's sort of supplementary to standard quantum physics. And we have this the space of hidden variables. So e.g. this would be the space of all possible measurement outcomes on your final hypersurface TS. So this is the one of the suppositions of this Kohlberg and Renner theory, but it's really saying is it Leaguewater? He's the one actually kind of putting it in this kind of formulation. And also you have mu here is a measure on your hidden variables. So it's just supposing that you have absolutely no knowledge about lambda, then the best that you can do is just take a weighted average of all your probabilities here. And it's assumed in this theorem that the measure on capital lambda is going to be independent on the measurement O hat. And so in this theorem it also assumes that parameter independence holds. And then what if you have these two things, then it means that the hidden variable probability of E hat is going to be the same as the quantum mechanical probability, sort of almost everywhere. And now this just seemed to be problematic insofar as, if you're going to propose a new theory of physical reality, and your physical reality not just in a measurable way, but it gives you exactly the same results from every kind of possible mathematical consideration. It just seems that coming up with your theory is just a complete waste of time. So really what you want for your addition to quantum mechanics is you want something that it does actually give you different results from quantum mechanics on the microscopic level, but when you actually average over all these, you get the same result as quantum mechanics on the averaged level, on the sort of macroscopic level. So that's really what you want from your addition. Otherwise you're not really adding anything significant to quantum mechanics. So this no-go theorem says that you can't have all these things that you really desire. You want to have this, and well, a lot of people are very wedded to the idea of parameter independence if you're going to have special relativity holding, and you want to have this not equal to this because you want your supplemented theory to be saying something new, whereas this suggests that your theory is not saying anything new at all. So it just becomes this identical really with standard quantum mechanics. One way to overcome this would be, as I'm sort of attracted to, is to say that, well, parameter independence violation is not such a big deal. I mean, of course, in some situations it really would be a big deal. I mean, maybe in the Bohmian interpretation, although the variables are called hidden variables, if it might be that eventually you could find some way of actually just really discovering these hidden variables, these locations, and then you really would have faster than light singling, because if you knew lambda, then you could work out what the actual measurements that they had made. But with Kent's interpretation, it just seems completely impossible that anyone really could know what this hidden variable was. So I don't particularly have any hang-ups if parameter independence holds, and I really do find it rather hard to see how parameter independence could hold in Kent's theory. Another way, if you really want to cling to parameter independence, then Another possibility would be to actually say that mu here is not independent of O hat here. And again, this seems you must have some kind of dependency of mu on O hat, because really this lambda here really encodes all the kind of experimental configurations that have been set up. So you wouldn't expect mu to be independent of O hat. So and in that sense, this integral isn't, I guess it's not really well defined, because here, you know, if you sum over all these, if you consider all these different possibilities, you can have all these different kinds of measurements that are going to take place. So, you know, you could just say that Holbeck and Renner's theorem, and those who've spoken more about it, this just really isn't at all relevant to what Kent has to say. But you know, this is probably not, for some people, this is going to be a rather bitter pill to swallow, because they're going to be people who really want to cling to parameter independence for the series to be consistent with special relativity. So I just briefly conclude. So Kent's theory can probably be developed into a theory that is experimentally indistinguishable from quantum theory. So when I say that it probably can be developed, because we've only been looking at toy models, so it doesn't seem to be beyond the realms of possibility that if we had a better understanding of quantum theory, then we could and further developed Kent's theory that they could be shown to be experimentally indistinguishable. And so the jury, according to Butterfield, is still out on whether Kent's theory violates parameter independence. But personally, and it's not obvious to me that if Kent's theory did violate parameter independence, then it would contradict special relativity. Okay, thank you.